In the last section on this fixed parameter tractable unit, we'll look at some further ways to show lower bounds for problems, so impossibility results. And what we've seen so far were W1 hardness reductions, where you could show a certain parameterized problem probably doesn't have any FPT algorithm. But what about problems where we do have some FPT algorithm, but we don't know whether we can further improve the functional dependence on K? So maybe let me spell this out. We had W1 hardness as the key tool. Probably not in FPT. And we had various techniques for designing fixed parameter tractable algorithms where that is not the case. How about problems in FPT? Can we somehow get lower bounds for this f of k? And of course, we'll pick on our favorite problem, vertex cover again. And remember, I had this on the slides previously. Vertex cover, we know algorithms with some constant 1.3 to the power k, the parameter, the threshold of the size of the vertex cover, times some polynomial in n. That was possible. Can we do better? So whatever the constant was, I guess here we can safely put an n squared, and that's going to be enough. Can we improve this further? In particular, this part. And maybe at first sight, it seems, okay, what else could you do? Like if the function it's unlikely that we can show some polynomial. That would be amazing, but then the problem would be in P, and we would have shown P equals NP. So unlikely is very unlikely. What else could it be? It seems sometimes that there's nothing between polynomial and exponential, but that is very, very not true, very untrue. There's a lot of things between polynomial and exponential. And I mean, there's things like 2 to the square root n, which is not quite, is smaller than any constant to the n, but is also not polynomial. Or there's quasi-polynomial, where you have 2 to the log to some power of n. Say 2 to the log to the 5n, which is essentially same as n to the log 4n. These are all running times that are, I guess I should have said k here instead of n, but as a function in n. These are all super polynomial, sub-exponential. And it's not clear if you can improve this to sub-exponential from what we've seen so far. All we have are upper bounds on this, and we have no lower bound for a vertex cover beyond probably not polynomial, okay? And that's what we're looking at here. Now, to make statements about this, you have to make a slightly stronger assumption than our standard P not equals NP or W1 not equals FPT. And these are usually grounded on some complexity theoretic hypotheses, and one of those is the exponential time hypothesis. It's often abbreviated as ETH. It appeared in some slides before. And formally it says, if that is true, it's a hypothesis. Nobody knows, right? This is unclear, but many people believe in this one. It asserts that there is a constant epsilon, so that every algorithm for PSAT, where it's parameterized by the number of variables, I guess it says what K is. I wish I would have said P variables, 3SAT. So every algorithm for the 3SAT problem requires some time 2 to the epsilon K. In other words, there is some 1 plus delta, and delta is greater 0. And we don't know what that constant is, but the hypothesis says there is one and it's not 0, so that any solution for the 3SAT problem, in the worst case, asymptotically and so on, needs an exponential time. Okay? So again, nobody expects polynomial here, but there's a lot between polynomial and exponential. But the exponential time hypothesis says, no, there's, for SAT, it has to be exponential, at least. And we know at most as well. Okay? Now, the hypothesis itself is a bit unwieldy because it only says there is such a constant. It doesn't tell us what the constant is. So it's a bit hard to refute or make sense of. Depending where you look, you can reformulate it. That's what I already said. The same thing is to say there is some delta, so that 3SAT algorithms need at least 1 plus delta to the k. Again, some exponential, just re-expressing how it's written. You could also say there's no way to have an algorithm with runtime 2 to the little o of k. So little o, again, was something that converges, some function that if you divide by k converges to 0. And that's not possible. And that is often the definition. So this 2 to the little o of k is usually what people describe when they say sub-exponential. Okay? That's why the name is called the exponential time hypothesis, because it assumes there's no sub-exponential algorithm for SAT. Alrighty. So far, that's just the definition. And the only thing I can tell you is that a lot of people believe that this hypothesis is sensible. And it seems any kind of algorithm for SAT has this property that it needs exponential time. So let's assume that this hypothesis is true. Or let's make this an assumption so that when we get some results, it would contradict this so that we assume the converse. That's how usual lower bounds work. So it's analogous to P and NP. We prove something is NP hard. What does that mean? Well, it means unless P and NP are the same, there's no polynomial time algorithm for that problem. And so we want to do the same thing with ETH instead of P equals NP, or P not equals NP. So we can use this to show that some problem X can be solved in some time that depends on some parameter of X. If that implies an algorithm that can solve the SAT problem in this time, so essentially contradicting what we've had for all possible epsilon, then that would refute the exponential time hypothesis. That's again the tricky bit. So this says there exists some constant, but it doesn't tell us what it is. So to refute that statement, we would have to show there is an algorithm for every possible epsilon that solves the SAT problem in this time. And in this case, so C, for example, could be a function of epsilon. It could, for any constant epsilon, n to the 1 over epsilon would still be a polynomial. but it has to decrease the base of the exponential part arbitrarily much. Okay. If we can do this, then unless ETH is false, we know that X doesn't allow such an algorithm. So we can try to kind of reduce problems to 3-sat and get algorithms of that running time for a contradiction. The thing is here, this seems tricky because it needs a reduction where the number of variables in the resulting formula is small. And that's not always the case, or at least in many prominent examples, it doesn't seem to work. This is a reduction I've kind of very, very quickly shown you at the very beginning. We talked about classical reductions. It's also one that you'll have seen maybe in some other places or in Karp's paper. It's reducing 3-sat to vertex cover. And it's just shown on an example. Here's some 3-sat formula, and you can turn that into a graph where you take, for every clause, you make a triangle with the vertices containing the literals of the clause. And the triangle are these blue edges, and then the bit that encodes the logic are the green edges, which are connecting every pair of literals that are negations of each other. So here I have x1, here I have not x1, that's why there's this green edge. Okay? And then the reduction says that this formula is satisfiable if and only if there is a vertex cover for this graph that picks exactly 2 vertices from each triangle. And you can easily show that you have to pick at least 2 vertices in each triangle, otherwise the triangle edges aren't covered. And if you need more, then that means that some of the green edges were not coverable by just picking 2 edges. So in a way, the literal that is true is the vertex that remains uncovered by the vertex cover, is not part of the vertex cover. You don't need to dig through the details for making sense of what follows. The thing is that here, the parameter that we generate is 2n. We need a vertex cover that's linear in the size of the formula. And if the formula has n clauses initially, then it'll have 2n. It'll have n triangles. So you need to take 2n vertices in your vertex cover. So before we can make sense of that, can we say something about the number of variables here? The thing is, it doesn't seem to matter, even if the formula has very few variables, the reduction wouldn't give you anything different. The reduction would still look the same and ask for a vertex cover of the same size. So it seems tricky to make this faster by if you were the number of variables doesn't seem to influence the reduction really. It's kind of ignored. Okay, maybe I can explain this bit, and we'll do the rest of the proofs next week. So far, this is what the exponential time hypothesis directly gives us is not good enough to do reductions of the sort that we can get lower bounds for the f of k part in FPT algorithms. There's a key structural insight, and unfortunately, the proof of this is relatively lengthy and a bit more intricate. So it's only available in the original paper. It's not unreadable, but it takes us too far. So I'm just stating the result without the proof. But I want to explain a bit what it does. And in a way, rewriting a certain 3-sat formula so that the number of variables and the number of clauses are similar. Formally, it says for every parameter epsilon that you give me, there's some constant that I tell you, so that I can take your 3-sat formula phi with n clauses and k variables, and I can give you an equivalent formula, so it's logically the same, logically equivalent, which is a big disjunction of many smaller 3-sat formulas. And I'm using the same k variables in these formulas, but each of these formulas only has capital K times little k clauses. So the number of clauses is linear in the number of variables of the original formula. Okay? Now, this sounds like a magic thing. The problem is that the number of these formulas that you need is exponential. You can control how many you'll get and how long the whole thing takes by specifying this epsilon. So the smaller you make epsilon, the larger this k will be, but then the time and the number of formulas is slightly smaller. But you have to pick a constant greater 0, so it'll be exponential either way. You can just control how small you want it to be. So we do 2 to the epsilon k such formulas psi, and the overall computation, I guess, is essentially linear in the output. Okay. Because I put this here, let me explain what sunflowers means. It's basically if you have a collection of sets, so say these are literals of some 3-sat formula. And maybe there's a lot of clauses that include the same literals, but have some other literal added on them. Maybe a nonsensical one too. So the algorithm essentially tries to find these sunflowers, so sets of clauses that intersect all in some 1 or 2 literals. And then it says you can satisfy all of those clauses by either satisfying their center or by satisfying all the petals. So you can either satisfy this or all of those 4 together. And that's where this disjunction of 3-sat formulas comes from. You get one part for the inner bit, either that is satisfied or the and of all the petals of what's left. And you need a clever recursive algorithm to make sure that you get rid of enough clauses that way. That's the part that's not very clean, or it gets very technical. Now let's, before we formally show this next time, let's briefly see why this is useful. The magic part here is that we take one 3-sat formula and get potentially many 3-sat formulas, but each of them is small in terms of the number of variables that we had before. And that ties nicely together to ETH. The exponential time hypothesis said nothing about the size of the formula, the number of clauses. It only considers the number of variables. But then it says it's exponential in the number of variables. With this sparsification lemma, we can take standard reductions like the one relating vertex cover and 3-sat, even if they're only generating something in terms of the size of the formula, number of clauses, we can still use reductions against the exponential time hypothesis, because each of these psi's is sparse in this sense that the number of clauses and number of variables are the same up to constant factors.